So when we talk about dealing with hypothesis testing and confidence intervals for two means, we have to break it down into whether they're independent or dependent samples. So we're going to start with the independent samples because that one's a tiny bit easier. We say two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with the sample values from the other population. And then if that doesn't happen, we say two samples are dependent or consist of matched pairs. If the sample values are somehow matched with each other. So this depends just solely on the type of study that has to be done for whatever thing you're dealing with. So what I'm going to do is I'm going to go through some situations where the data is similar, but we're going to see which of them is independent versus which one is dependent or matched pairs. Okay. And it doesn't necessarily mean the one probability affects the other. It's just there's a connection between the two. So for independent, that could be the heights of men and women. So you might be comparing those means in some way. Okay? So there's no connection from the two different populations. However, if I change this slightly and change this to the heights of husbands and wives, now there is a connection between those two different groups. So this would be dependent data. Okay? If we think about medical trials, well, in one case you can have a control group, one case you have a treatment group. There's no connection between those and no match data. So that would be an independent sample. So this is a medical trial with a control group and a treatment group. Those are independent groups. But if I look at a different medical experiment, maybe we're doing a drug trial and we want to see the before and after effects of a particular drug. In that case, the data is paired because it's based on that individual. What was their mean before? What was their mean after? Or what was the sample before of maybe blood pressure? What was the sample after going through that drug trial? So here, before and after data is dependent. Okay. So for independent data, it's very possible that your sample sizes for the populations are different, but they could be the same. Kind of like in the one example, it happened to be they pulled the same number of gloves for each. So this may be the same sample size for each population, but it's not necessary. When you're dealing with dependent data though, because there is a matching, these must be the same sample size. Each data is matched up, so it's going to be the same for both, okay? So we're gonna start with our independent, and then again, we'll move on to dependent afterwards. It's still gonna follow the same process, it's just you have a different approach to find the test statistic that you want. And again, when it comes to matched, that one's a little bit more complicated to get the test statistic. You have some more work you have to do. So in terms of notation, it's the same when we were dealing with hypothesis testing for one mean. The only difference is you use a subscript to indicate the population. So mu1 is going to be the population mean for that first population. Sigma 1 is the population standard deviation. N1 is the size of sample 1. X bar 1 is that sample mean. And S1 is the sample standard deviation. And then all of those, you can replace the 1 with a 2 for the second population, okay? In terms of requirements, we have a few that need to be met. The first is that both of the true standard deviations for the populations are unknown, and we do not assume they are equal. If they're equal, it's a completely different test statistic, and we're not even going to get into that particular case because it's very unlikely that they are equal from the two populations. The other in this case is we're going to look at the samples being independent. And then that third criteria is the same one as before. You want the samples to be large, meaning both samples are greater than 30, or both those samples come from normal distributions. Okay, as long as one of those is satisfied, you're good. Because this is where we're going to use our t-distribution. When we deal with means, typically we're going to do that t-test for it. So here we're going to look at a null hypothesis being that the means are equal. In this way, their difference is going to be 0. So same thing as before with proportions. So the only difference is you still can test whether one mean is greater than the other, but your null hypothesis is that these two are going to be equal. The actual test statistic follows just from the test statistic for a single population. So just to refresh what that is, it was the sample mean minus the true population mean over S over root N. And remember, this mean came from the claim itself. So in our case, this is going to be 0 because we're looking at the differences. So our test statistic is going to be a t-value, and we're going to be using that t-distribution, which is based on the degrees of freedom. We need to look at the difference in our sample versus our true. So in this case, our sample is x1 bar minus x2 bar, and then minus the true. But again, it's going to be that we're assuming these two are equal, so this is going to be 0 in all of our cases, okay? And then we divide this by a square root. What would happen is this was originally under a square root to just get the standard deviation, so it dealt with the variances. But here, because we have the 2, it's not going to simplify, so we have something nice in the top. What happens is we have to take the first variance, sample variance, and square it, and divide it by its population size. And then we need to add the same thing with the second sample. Okay. So again, very similar to the bottom here, because you can put this under a square root of s squared. But because we have the 2 different samples, we need to take both of them into account, okay? So this is our test statistic. Once we have that test statistic, we're gonna use technology to find the value of P, or we can use that student t-distribution table. But again, for finding p-values, you're gonna have to use technology for us. Really, the only thing we can use the table for is finding critical values. So that's based on the significant level and whether it's 1 tail or 2 tails, and you can find the area or where those rejection regions are going to be. The one thing we do need to figure out is when we have 2 sample sizes, our t-distribution is based on the degrees of freedom. But because we have 2 sample sizes that don't necessarily have the same amount, we have 2 degrees of freedom for each one. So the way we find the overall degrees of freedom is we take the smaller of the 2. So it's the smaller of the first sample size minus 1, which is its degrees of freedom, and the degrees of freedom for the second population, okay? So i.e., this is just the smaller of the degrees of freedom from the samples. So if our first sample has 50, our second sample has 60, well, I'm going to use the degrees of freedom from the smaller amount, so it would be from the 50, so my degrees of freedom would be 49, okay? In terms of finding my confidence interval, we really, again, take that estimate we have with it and we add and subtract that error, and that error is going to be based on that critical value of t. So if I'm looking at what the true difference in means lies between, it's based on that estimate for each plus an error, and then the estimate for each minus the error. Where your error is found by taking that critical value associated to that confidence level, which we're going to use our chart for, and timesing it by a square root. And what goes in the square root is really exactly what's in the denominator here. So this is going to help us estimate that standard deviation for the whole thing. So S1 squared over N1 plus S2 squared over N2. Okay. So we're going to do two different examples. For this one, we're going to start by working with a claim, and we're going to test that claim using a hypothesis test, and then do the same thing by doing a confidence interval. So in this example, we're told, given in the table below are the BMI statistics for random samples of men and women. Assume the two samples are independent random samples selected from normally distributed population, and do not assume that the population standard deviations are equal. We want to use a 0.1% significance level to test the claim that males and females have the same BMI, okay? So they give me all of my data here in a nice little chart. My first population is males, my second population is females, and I want to test the claim that their true means are equal. So our claim here is that mu1 is equal to mu2. So that is exactly our null hypothesis, which means that the difference in these two is going to be 0. And then our alternate is that these two are not equal to each other. So we want to use a 0.1% significance level. So this, because of that alternate hypothesis, is going to be a two-tailed test, where alpha is going to be 0.01. So for this one, we're going to go through it both ways. We're going to use an online calculator to find the p-value, but during a testing situation, you might not have access to that. So in that case, we'd have to go through the critical value method. So I'm going to show you both on here. So we're going to start by finding what is our test statistic. So just to copy all of that down, our value of t is the difference in the sample means minus the difference in our population means divided by a giant square root. And in the bottom, that would be S1 squared over N1, and then S2 squared over N2. So first, the difference in these two, we're assuming to be 0 because we're assuming these are equal to each other. Filling in our other pieces, X1, they tell us is 28.0478. And X2 for women is 26.5097. And then here in the bottom, I got some big numbers to square. So I need lots of room. S1 is 8.356213, and we're going to square it. And N1, need to go back up a little bit, is going to be 49. And then for this, S2 is 4.764252 squared. And N2 happens to be the same thing, which is 49. Okay. So for time's sake, you can plug this into Desmos or a calculator. You should get that this is 1.13. Okay. So that is my test statistic. And then my degrees of freedom, we need to find as well. So if I look at each population for the men, that degrees of freedom is the sample size, which is 49 minus 1, which is 48. And for women, our degrees of freedom is the same thing because these two sample sizes happen to be the same. So overall, my degrees of freedom is going to be 48 because it's the same. So going through my online calculator, this one's from Social Science Statistics. My t-score that we just figured out is going to be 1.13. My degrees of freedom is 48. This is a significance level of 0.01, and it is a two-tailed test. So plugging that in, my p-value is 0.264091, okay? So rounding that to a few decimal places, that looks absolutely terrible. This p-value is 0.264. Okay, a little nicer looking now. Okay, so here, this p-value is bigger than my significance level. So that means I fail to reject the null hypothesis. So the area over here is going to be bigger than that rejection region. Okay. So since our value of p is greater than or equal to our significance we wanted, we fail to reject the null hypothesis. So there is not sufficient evidence to warrant rejection of the claim. So again, that doesn't mean that we support that the two BMIs are equal to each other. It just means I can't reject it, okay? So that's using our p-value, but again, I have to use an online calculator for this method. I cannot use a table. So instead, if I have to do this by hand, I'm gonna use the critical value method instead. So I'm gonna show you how to do that one as well. So our degrees of freedom is still 48. Our significance level is 1%, and it's the area in two tails. And then our critical value is what we need to find. So drawing a little picture as what's going on here. For our t distribution, we have symmetry, these are the two critical values that define my rejection region. And if the test statistic falls in this rejection region, that's when I can reject the null hypothesis. And again, I have symmetry, so right here in the middle is equal to 0. So I need to go to my table and I need to figure out what is that critical value. So that's all the way at the end down here. So my area in two tails has to be 1%. So I'm going to be using this particular row. And then my degrees of freedom is 45. But if 48. If I scroll down, I don't have a 48. So I either need to use 45 or 50. So that's where we always play it safe and we go with the smaller amount. So my critical value is going to be right here at 2.690. Okay. So going back up, my degrees of freedom, we need to use row 45 because there is no row 48, and our critical value is 2.690. So this value is positive 2.690. This one is negative 0.2690. Look. And then our test statistic, going back up here, we already found it. It's 1.13. Well, 1.13 is somewhere over here. So since this test statistic doesn't fall in the rejection region, we fail to reject the null hypothesis. So same exact conclusion that you'd get to make, okay? But easier to do because we're finding those rejection regions. The other thing we can also do is instead we can construct a confidence interval to test this particular claim. And then we're going to see, does that contain 0 or does it not? Okay. So for the second part, we're going to do the same thing, but we're going to construct a confidence interval suitable for testing this claim. So if I want to test that these two means are equal to each other, I'm going to look at their difference. And I want to see, does that difference contain 0? Because if it does, then there is a good chance that the means are equal, or there is a chance of it. So what I do is I use, again, the estimates for each mean, add the error, and then same thing, minus the error. Where, in this case, the actual error is going to be some critical number multiplied by the same thing that was in our denominator, S1 squared over N1 plus S2 squared over N2. So really, this critical value is going to be exactly the same one from up here. You find it the same way. So your alpha is 1%. Those are the two cutoff values. So you use that first row in the table. And then my degrees of freedom is 48, but I don't have a row for that. So I use 45. And this tells me that my critical value is 2.69. So this area here, half of each of these, this would be 0.5%, and this would be 0.5%. So it is the same critical value we found before. Okay. So T alpha over 2 is the same critical value because you use the same information to find it. So this is 2.690. So I have everything I need to find my error. So this is going to be 2.690 times this square root. S1, going to avoid scrolling back up, that's 8.356. and then it's got some change in it, but I'm just gonna go to 3 decimals, and that sample size is 49, and S2 is 4.764, and its sample size is 49. So if you plug this in your calculator, this should give you about 3.696. So that would be my error. So my confidence interval with 0.01 significance results in the 99% confidence interval. Our true difference in these two means, just going to copy what we have up here, is bounded by the samples plus an error, the samples minus this error. So filling in the values we have, x1 is 28.048, x2 is 26.510, and the error we found out to be 3.696. And then doing the same thing over here, it's the same numbers, but minus, and it barely fits on one line. So if you plug those into your calculator, this should give you 5.234 on the upper bound and negative 2.158. So again, the claim that I'm making is that the two means are equal, so their difference is equal to 0. So if I look at my confidence interval, that contains 0, okay? So because of it, I cannot reject the null hypothesis. There is a possibility that the means, the difference in means is 0, meaning the means are equal. So since the confidence interval contains 0, we fail to reject the null hypothesis. Okay. To just analyze again what it would mean if these were both positive, that would indicate that the means are not equal to each other. And in this case, because they're both positive, this first mean would have to be bigger. So that would mean males have a bigger BMI than females. If both values were negative, and this doesn't particularly make sense because these two would have to be switched, but if they were both negative, again, 0 does not fall in that interval, so the means are not going to be equal to each other. And in that case, because of the negative, that would mean this quantity has to be bigger, and females would have a bigger BMI, okay? All right, so we will see an example of that a little bit later on, but for now, let's try another example testing the claim. So we're not gonna go through a confidence interval in that one, we're just gonna go through and do the critical value method. So we're told a magazine claims the mean amount spent by a customer at Burger Stop is greater than the mean amount spent at Fry World. The results for samples of customer transactions are shown below. At a 5% significance, can we support the magazine's claim? And we're gonna assume the standard deviations are not the same, okay? So our claim is the mean amount at Burger Stop is more than that at Fry World. So our claim, population 1 is Burger Stop. We're claiming that is bigger than Fry World. Because it does not have inequalities, that means this is the alternate hypothesis. And the null then is that these two are equal, or really less than or equal. So based on our alternate, this is going to be a one-tailed test, and specifically a right tail. Our significance level is 5%, and it is a right tail. Okay. So I'm going to start by finding my test statistic. So just to write all of that down, our value of t is the difference in the sample means minus the difference in the true means over a giant square root, which is the standard deviation of sample 1 squared over its sample size, and then the same thing with the second sample. Because we're assuming for the null hypothesis these are equal, this one is going to be 0. So plugging in our information, the mean of x1 is 11.63. The mean of x2 is 11. And then in the bottom, we've got the square root. S1 is 0.79, so we square that over its sample size, which is 13. S2 is 68 cents over its sample size, which is 11. And again, at this point, I'm going to trust you can plug this into your calculator. Our test statistic is 2.099. Okay. So I want to find my critical value now, so I can find that rejection region. So here, if I go ahead and kind of just copy my image for my type of test, I need to figure out what is this value down here, t. In order to do that, I need to find my degrees of freedom. So for Burger Stop, that sample size is 13. So my degrees of freedom is 1 less, which is 12. For Fry World, my degrees of freedom, the sample size is 11, so -1 is 10. Which means the degrees of freedom we should use is the smaller amount, which is 10. Our alpha, our significance level, is 0.05, so that needs to be the area in one tail. And so those two things alone give me exactly how to find my test statistic. So my area in one tail, which is up here, is 0.05. So I'm going to look down here until I get my degrees of freedom being 10. So my critical value is going to be 1.812. So this value of t is exactly that, 1.812. So if anything falls to the right of that, that's where we are going to reject the null hypothesis. And in this case, our test statistic is 2.099. So since the test statistic falls in the rejection region, we do exactly that. We reject the null hypothesis. And the null hypothesis is that these two are equal to each other. So that means there is enough evidence to support the claim, which is that the mean value at Burger Stop is more than the mean value spent at Fry World. So the magazine was making a fine claim. So we'll do some more examples with now matched pairs. Again, those take a little bit longer because you have to find some intermittent things before you can find test statistics.